Einstein's theory of general relativity tells us that gravity is not a force, but a curvature in spacetime caused by massive objects. This revolutionary idea changed our understanding of the universe, showing that what we perceive as the force of gravity is actually the warping of the fabric of spacetime itself. Imagine a bowling ball placed on a trampoline. The weight of the ball causes the fabric to stretch and create a dip. The ball creates a dip, distorting the fabric of the trampoline. This is a simple analogy to help visualize how massive objects like planets and stars warp spacetime around them. Similarly, massive objects like stars and black holes create dips in spacetime. The more massive the object, the deeper the dip and the stronger the gravitational pull. This curvature of spacetime affects time itself. The presence of a massive object can actually slow down the passage of time. Time flows slower in stronger gravitational fields. This means that near a massive object, time ticks more slowly compared to a region with a weaker gravitational field. This phenomenon is called gravitational time dilation. It is a direct consequence of the warping of spacetime. The closer you are to a massive object, the slower time passes for you relative to someone farther away. This effect becomes more pronounced the closer you get to the object. Think of it like this. Imagine two identical clocks, one on Earth's surface and one in orbit. The clock on the surface, being in a stronger gravitational field, will tick more slowly. The clock in orbit, further away from Earth's gravitational pull, will tick slightly faster than the clock on the ground. This difference, though minuscule, is measurable. This difference in time is incredibly small, often just fractions of a second over long periods. But it has been experimentally verified using atomic clocks. These highly precise instruments have confirmed the predictions of general relativity. Gravitational time dilation means that time is not absolute, but is relative to the strength of the gravitational field. This challenges our everyday experience of time as a constant, unchanging flow. This concept has profound implications for the possibility of time travel. If we can manipulate gravity, we might be able to influence the flow of time. It suggests that by manipulating gravity, we might be able to manipulate time itself. This opens up fascinating possibilities for future technologies and our understanding of the universe. Wormholes are another intriguing concept from Einstein's theory of relativity. They offer a potential shortcut through spacetime. Imagine a sheet of paper representing spacetime. Now fold the paper in half and punch a hole through it. The hole represents a wormhole, connecting two distant points in spacetime. Theoretically, a wormhole could connect two different points in time as well as space. Traveling through a wormhole could allow us to reach distant galaxies in an instant, or perhaps even journey to the past or future. However, wormholes remain highly speculative. They are theoretical constructs based on solutions to Einstein's equations. We have never observed a wormhole directly. Their existence is still debated among physicists. Even if wormholes do exist, several challenges would need to be overcome to use them for time travel. They might be incredibly unstable, collapsing before anything could travel through them. Additionally, the amount of energy required to create and maintain a wormhole could be astronomical. Section 4. Loops in time. Closed time-like curves. Closed time-like curves are theoretical paths through spacetime that loop back on themselves. Imagine following a path on a flat surface. You would eventually return to your starting point. This is analogous to a closed time-like curve, but instead of looping through space, it loops through time. If such curves exist, they could allow for time travel into the past. However, closed time-like curves raise significant paradoxes. The most famous is the grandfather paradox. What would happen if you traveled back in time and prevented your grandparents from meeting? You wouldn't exist to travel back in time in the first place. These paradoxes suggest that closed time-like curves might be physically impossible, or if they do exist, they might be governed by rules that prevent such paradoxes from occurring. For example, some theories propose that the past might be unchangeable. Any attempt to alter it would simply result in a new timeline branching off. Section 5. Surfing Spacetime, the Alcubierre Drive. In 1994, physicist Miguel Alcubierre proposed a theoretical concept known as the Alcubierre Drive. This concept envisions a spacecraft that could achieve faster-than-light travel by warping spacetime itself. Imagine a surfer riding a wave. The surfer doesn't move through the water as much as they are carried along by the wave's motion. Similarly, the Alcubierre Drive proposes creating a warp bubble around a spacecraft. This bubble would compress spacetime in front of the ship and expand it behind. By riding this wave of distorted spacetime, the spacecraft could theoretically travel vast distances in a shorter amount of time. This form of travel wouldn't violate Einstein's theory of relativity, as the spacecraft itself wouldn't exceed the speed of light within its local space-time bubble. While mathematically sound, the Alcubierre drive faces significant hurdles. It would require a type of exotic matter with negative mass-energy density, something we've never observed. Additionally, the energy requirements for creating and maintaining the warp bubble are astronomical. Section 6. Dreams of Tomorrow. The reality of time travel. The concepts we've explored offer a tantalizing glimpse into the possibilities of time travel through the manipulation of space. Imagine bending the very fabric of reality to journey through time, a notion that has captivated human imagination for centuries. However, it's crucial to remember that these ideas are still highly theoretical. The equations and theories that scientists work on are complex and often lead to more questions than answers. Gravitational time dilation is a real phenomenon, but the time differences involved are minuscule over human lifespans. For instance, astronauts on the International Space Station experience time slightly slower than we do on Earth, but the difference is just a fraction of a second. Wormholes and closed time-like curves are intriguing solutions to Einstein's equations. These concepts suggest pathways through space-time that could, in theory, allow for time travel. However, their existence is far from proven, and they present formidable challenges. The energy required to create and sustain a wormhole, for example, is beyond our current technological capabilities. The Alcubierre drive, while theoretically possible, relies on exotic matter and energy sources that we have yet to discover. This hypothetical propulsion system could, in theory, allow faster-than-light travel by contracting space in front of the ship and expanding it behind. Time travel, while a fascinating concept, remains firmly in the realm of science fiction. Popular culture is filled with stories of time machines and paradoxes, but these remain speculative. Yet, the pursuit of understanding time travel pushes the boundaries of our knowledge. It drives scientists to explore the very limits of physics and cosmology, seeking answers to some of the universe's most profound questions. It challenges us to think beyond our everyday experience and consider the universe's true nature. What is time? Is it a linear progression, or could it be more fluid and malleable than we ever imagined? While we may not have time machines yet, the quest to unravel time's secrets continues to inspire and intrigue us. Each discovery, no matter how small, brings us one step closer to understanding the cosmos. As we delve deeper into the mysteries of the cosmos, who knows what wonders we might uncover? The journey of exploration is just as important as the destination, and the pursuit of knowledge is a never-ending adventure.